Hi, I'm Maxwell Mamishev, and in this video, we're going to explore how modern radio astronomy uses passive electromagnetic sensing to search for extraterrestrial life, and how we're using those same techniques now to find unidentified anomalous phenomena, UAPs, which are kind of like the rebranding of UFOs, in our own planet's ionosphere. So I'm spending the summer here at UC Berkeley. There's a nice tower in the back. I'm wearing the shirt, right? At the Search for Extraterrestrial Intelligence, SETI, Research Center through their Breakthrough Listen initiative. So here at SETI, we focus on looking for technosignatures, indicators of advanced civilizations in the form of radio signals. One of the primary tools in SETI research is this Allen telescope array in Northern California. And it's an interferometer that consists of 42 6-meter dishes. They're pretty big and pretty expansive. There's a 43rd one somewhere over there. Right over there behind me on the ground. Well, that one's planned to be put up soon. And it looks for signals in the 1 to 10 gigahertz band. There's also instruments like this Green Bay telescope, which uses a single large dish that's nearly 150 meters tall, and it's out in the NRQZ, that's the National Radio Quiet Zone in West Virginia. There's a lot of complexity in how these tools are used to search for aliens, but they'll give you a short, simple understanding of one way that we do it. So this is a process that's used with a lot of data from the Green Bay telescope, for instance. We would look at a target for 5 minutes, look away for 5 minutes, and then repeat this 3 times. Overall, this is called a cadence. It takes 30 minutes to do. 3 times 5 on, and then 3 times 5 off. And if a signal consistently appears when we're looking at the target and disappears when we are not looking at the target, then we know that we have found something. A lot of the time, that something is radio frequency interference, RFI, actually almost all of the time, because if we found aliens, we would have told you by now. So there's a massive effort to explain why most signals that we find are radio frequency. Actually, that's most of what SETI does, just looking at different signals and trying to reason out, no, this isn't aliens because it's this or it's that. Their instruments were off, or it was Elon Musk's Tesla floating up there that we detected, and yeah. So when we look with this telescope, we plot this data on a spectrogram. It has time on one axis and frequency on the other. And SETI projects like Breakthrough Listen use high-resolution spectrograms and automated filters to sift through these petabytes of data, trying to isolate candidates for signals that could be extraterrestrial intelligence, aliens. Very exciting, right? Here is one spectrogram of data that is actually extraterrestrial intelligence. It's nearly 20 billion kilometers away, and it's the Voyager 1 probe that we sent out in 1977. There's a radio transmitter on it. It's very small, and it uses about as much power as the light bulb in your refrigerator. But we're still able to detect it loud and clear, which is amazing. My project with Zheng Liu from University of Washington and some other people is provisionally titled Nimbusort, and it uses a similar technique to answer a different question. Can we use these RF frequencies and this radio data with spectrograms and such to identify unidentified anomalous phenomena, or UAPs? We talked about it a little earlier. It's like the rebranding of UFOs. When I say UAP, I do not mean an alien spaceship that is creating crop circles and abducting cows and such and such. I'm talking about an object in the atmosphere that we just haven't identified. We're aware that something is up there, but we don't know exactly what. This is just a government term in place of UFOs to extend the definition of anomalous phenomena to include space and sea, although the vast majority of what we're looking at is still in the air. So to be a little more specific, the US government's Department of Defense's All-Domain Anomaly Resolution Office, AARO, states, unidentified anomalous phenomena, UAP, means A, airborne objects that are not immediately identifiable, B, transmedium objects or devices, like satellites that start in space and fall down to Earth, or C, submerged objects or devices that are not immediately identifiable. The DoD considers unidentified anomalous phenomena as a source of anomalous detectors in one or more domain. So I know this might have been a mouthful, but it's important to clearly define this so that there is no confusion. This is not about aliens on Earth or extraterrestrial technology. From their fiscal year 2024 Consolidated Annual Report on Unidentified Anomalous Phenomena, AARO reported around 700 UAP events, and only about 1/3 of these reported events were resolved. Of those, 70% were identified as balloons. The majority of AARO's case holdings remain unresolved due to a lack of data needed to further analysis. Without sufficient actionable data, these cases cannot be researched or analyzed. So now back to Nimbusort. The basic concept is pretty simple. When meteors, rockets, space debris, or other objects fall through the ionosphere at roughly 50 to 1,000 kilometers above sea level, they generate electromagnetic fields, which in theory can be detected by antennas. Our team deployed an antenna system in West Virginia to capture these electromagnetic signatures generated by phenomena like rockets, meteors, re-entering space debris, and other things that can be classified as UAPs. These events often create transient ionospheric disturbances, which means that they emit brief but very detectable radio frequency signatures. You might notice a major issue here. There are tons of radio signatures in our atmosphere. It's one of the things that SETI struggles with most in other radio astronomy projects. It's filtering through RFI. There's Wi-Fi, AM radio, FM radio, TV broadcasting, and other radio astronomy projects. You can look here at all these US frequency allocations. It's crazy, right? So how do we isolate these objects and phenomena among this myriad of other signals? Well, it has to do with where we're looking in terms of frequency. We're looking here in the very low frequency, ultra low frequency, and extremely low frequency bands. More or less anything under 30 kilohertz. In this range, the only people broadcasting are pretty much in submarines, and we're not looking for signals underwater. So we can take a signal from an antenna, put it through a few analog filters, a field programmable gate array, FPGA, and run a fast Fourier transform with some Turkey window, then generate a spectrogram with a frequency on one axis and time on the other, and a gradient of intensity. Take this spectrogram, for example. This was detected by our antenna. It's a very low frequency signature of meteor entry event 3646 2024 in the International Meteor Organization's Fireball database. It's a very clear signature, and it was reported at practically the same time as the meteor. And here is a signature of one of SpaceX's Falcon 9 launches. There are very observable differences in these spectrograms, especially visible in these diagonal patterns and exponential decay of the signal. So why does this all matter? Using an antenna to search for aliens or electromagnetic sensing to look for objects falling through our ionosphere. Well, let's start with the implications. Passive electromagnetic monitoring is of major importance to detecting aerial phenomena. There's many other systems like cameras or magnetometers that also do a great job in detecting things, and this is another tool in the arsenal to be added for detection of these phenomena. I think these specific VLF antennas are very powerful because they can operate in practically all weather conditions without requiring a line of sight to their target or an active signal. It makes them ideal for monitoring high-altitude space debris reentries, meteor showers, or other atmospheric anomalies in remote areas where other systems are falling short. They're also passive. It means that they don't emit any signals, and they don't interfere with any other equipment, they don't create any RFI, and they don't require any special licenses to use. It makes this kind of sensor perfect for use in civilian airspace or in remote observatories. It's something which can just be set up and taken down. I'm very hopeful on the potential of this technology to improve atmospheric science and maybe even prevent misclassification of events that would otherwise go unexplained. When paired with data from other sensors like cameras or magnetometers, this could become a very powerful tool in better detecting and classifying UAPs, especially when over 90% of reported UAPs are occurring in the ionosphere between 5 and 60 kilometers above sea level, exactly where we're looking. So now for the future work in this direction. So the next phase of Nimbusort is building a robust classification system, possibly using machine learning algorithms. The spectrograms that we've collected so far could be used to train AI models like convolutional neural networks or random forests, which can better sift through data and detect hits, identify meteors, possibly at rates better than humans. And these AI tools have been shown to be better than humans at understanding large data sets. So my hope is that they can help us detect anomalous events more often, and then more than that, tell us what exactly occurred when, and where. So another exciting piece is geographic expansion of these sensors, putting identical sensors in multiple locations. If we did this, we can better triangulate signals and understand not just when an object is in the atmosphere and what kind of object it is, but also get an idea of roughly where it is at any point in time. This additionally helps reduce false positives from having only a single sensor and allows us to make more precise maps of these events, like ionospheric disturbances, meteor trails, or potential UAPs. In a world increasingly filled with noise, the ability to detect subtle, unexplained signals matters. And whether it leads to finding ETs or UAPs, the science is worth doing. Thank you for watching. This video is based on my paper, Nimbusort Advanced Classification of Atmospheric Events Using Electromagnetic Signatures. It's planned for publication at the MIT URTC 2025 conference in October, and I hope it becomes the first of many publications in this research direction, as it provides a solid groundwork for future projects. Many of the visuals include data from my fieldwork at Hat Creek Radio Observatory, where the Allen Telescope Array is, a lot of public SETI resources and ARO resources. If you're interested in finding more about this direction, please see the sources in the description. They act as great jumping off points for better understanding any of the topics discussed in this video. So I'm Maxwell Mamishev. Thank you for watching. I hope you learned something.